Perceptrons are used for machine learning representations in terms of modeling data. What I mean by that is we have an x-axis and a y-axis, and I guess we could represent the graph as a one-dimensional graph, because there's only one x value. So if there's two x's or two x-axes, then it's two-dimensional. If there's three x-axes, then it's three-dimensional, and so on. So we have data that we plotted, and we could represent the data as x1, y1, comma x2, y2, dot, 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 to xn, comma yn. And this is the first data point or sample. This is the second data point or sample. And this is the very last one, the very last data point or sample. And for linear models, we have to include a threshold value where x sub naught, that represents the threshold value, which equals 1. So I guess if we wanted to be very specific, we would include within this list of values the data point that represents the threshold as x sub naught, comma y sub naught, where x sub naught is this, is x sub naught is equal to x sub naught, and 1 is equal to y sub naught. So we could just plot these values arbitrarily, making a scatter plot. And what the perceptron learning algorithm does, draws a line. That's what's called a linear model, because it's trying to linearly separate the data into two segments. And let's just say that we wanted to just get yes or no outputs on these data points. And this given perceptron boundary, where x sub naught, that represents the threshold value, which equals 1. So I guess if we wanted to be very specific, we would include within this list of values the data point that represents the threshold as x sub naught, comma y sub naught, where x sub naught is this, is x sub naught is equal to x sub naught, and 1 is equal to y sub naught. So we could just plot these values arbitrarily, making a scatter plot. And what the perceptron learning algorithm does, draws a line. That's what's called a linear model, because it's trying to linearly separate the data into two segments. And let's just say that we wanted to just get yes or no outputs on these data points. And this given perceptron boundary generates this segment. So let's just say that the data was perfectly linearly separable, meaning that the perceptual learning algorithm perfectly separated the data into its appropriate groups without having a data point incorrectly overlap into the other group. So it's perfectly separable. So that was just like an illustration of what, or a snapshot of what the perceptual learning algorithm is. So with linear models, we have this issue of input representation. and this is specific towards supervised machine learning. Supervised machine learning. So we have the input data and the output data, and we're trying to generate an appropriate learning model based off of our labeled historical data. So let's just say for our given data set, we have a set of written numbers that we got from the post office. So it's really important for you to get real data to test off of. It's just like a principle when you're doing machine learning. You always want to get data that was generated by real life circumstances. So let's just say that we got a set of zip codes that was from the post office. We have 93010, 90210. We have 80215, and so on. Let's just say we got, n data samples, and this is like n1, n2, n3, all the way down to n. Now you see that, this 9 looks kind of weird, this 3 doesn't look like a perfect 3, and this 5, may not necessarily look like a 5. And we want, let's just say that our given application for our learning model is to correctly classify each number within the zip code, so a serial of numbers, and we want the machine learning algorithm to classify each number within that serial correctly so that we can identify the correct location or zip code for that given sample. Well, if we listed each number, let's just take, for example, this number 9, a matrix of pixels, and we could say that each number, numbers 0 through 9, represent a matrix of 16 by 16 pixels. So this number 9 right here, when you represent it, contains 16 by 16 pixels, meaning that you have 256 total unique numbers to represent this number 9 in all nines, in all numbers, in all nines, in all numbers from 0 through 9. That's a lot of values to represent for your features. So each pixel would represent a feature, and this would actually exclude the threshold value that we mentioned earlier. So in reality, if we want to tack on the x sub naught, then it would be 257 values that we would have to represent within our given input. We want to actually lower that because we want to reduce the work that our given algorithm has to do, because first of all, it sort of improves the speed of the algorithm to generate its model or pick its best final hypothesis function. And also, when you're learning, there's an implied trait that the data is general. You don't want to overfit the data because it might perform really well in sample, but it might do poorly out of sample. And so you want to minimize that risk of happening, that risk of your learning model doing poorly in the outside world, by making the inside world model general. So how do we do that? Rather than picking our features based on the total number of pixels, we could pick the features by like a higher dimension feature. So instead of pixel value, we could say, well, what's the symmetry and the intensity of each digit? So if you had a 1, the number 1, if you flip it over, if you flip this 1 over, then the symmetry would rate pretty high, meaning that we would get a low difference between the 1 standing up and the 1 standing upside down. We would get a very low number, and that would generate a unique value for that degree of symmetry. And that degree of symmetry would be different for the number 2 and 3 and 5 and 0 and 9, so on and so forth. So we could use the value of symmetry as a unique feature to classify a digit rather than having to deal with 257 total unique values. So if we wanted to find another high dimension feature, we could choose the intensity. So if we choose 1 as an example again, the number 1 in terms of covering surface area would be relatively low in comparison to the number 5, which would cover more surface area than the number 1.